B and Jagatap for his presentation on the thermophysical and thermochemical evaluation of prospective thorium fuels for advanced reactors. Dr. Jagatap is presently director of the chemistry group, BARC. He is expert in high-resolution spectroscopy, laser cooling, and trapping of atoms.
Thank you, Mr. Chairman.
Floor is yours.
And let me thank my friends, the organizers, Dr. Vijayan and Dr. A.K. Naik, for giving me this opportunity. Friends, I shall be describing here about decades of exhaustive work carried out by my colleagues in chemistry group in thermodynamic and transport properties evaluation for the thorium-based fuels for the advanced reactors. Since the work is really exhaustive, I shall be giving you only a bird's eye view. Well, as we know that the fuel options for thorium-based reactors are ceramics, metallic alloys, and the molten salts. In this presentation, I shall be describing the thoria-based fuels for HWR, the thermophysical assessment, thermodynamic and transport behavior, and release behavior of fission gases and volatile fission products. And then we go over to the thorium-based metallic alloy fuels. These are the potential fuels for the advanced reactors. And here I shall briefly describe the preparation, characterization, and some thermophysical assessment. And finally, we go over to the conclusions and the way forward. All this in the evaluations, the database that we generate is using the indigenously developed facilities. This is the Knudsen diffusion apparatus, the thermal conductivity setup, the transpiration system, high temperature dilatometer, and the post-irradiation learning facility. The thermophysical characterization for the HWR fuels, well, this is all well known that the fuel behavior depends on the thermophysical properties, and these are the essential inputs for the fuel design, performance modeling, and developing safety analysis code. And these are the properties we seek, the thermal conductivity, thermal expansion, so on and so forth. And the variables are composition, temperature, porosity, microstructure, etc. This is just a view graph to show what kind of ranges that we are working in terms of the thermal conductivity. In specific case for the thermal conductivity, important for the center line temperature profile and also the behavior of the fuel under power ramp, and it varies dynamically during irradiation. This was discussed by Dr. Mehta in the morning. The fission gas bubble formation, porosity, fission behavior, product buildup, stoichiometry, etc. And what we have studied, this was part of the task force on the thermodynamic and transport properties of HWR fuels. A host of fuels, and including the SIM fuels, have been studied in this program. For example, here is the thermal conductivity results. Since we are using the indigenously developed equipments and getting the high quality data, this is the representation. This is the thermal conductivity of UO2, and you can see how our results match beautifully with the other results. And this is the result for thoria and the thorium uranium oxide. And we have built the indigenous database with the in-house synthesized fuels. This one was shown by Dr. Ramkumar. As the thoria lanthanum content increases in the fuel, the thermal conductivity or the temperature decreases. So the lambda deteriorates with the buildup of thoria rare earth oxide solid solution phases, and one which has not been shown here, that it also increases with the precipitation of metallic phases. The thermal expansion, it is required for the stress estimation and also for the gap conductance and the store energy. The methodologies followed here are the bulk thermal expansion, lattice thermal expansion. The variables are temperature, composition, density, microstructure, and the host of fuels have been studied in this program. These are some data that we have generated on the lattice thermal expansion of HWR fuels from room temperature to 1473 degrees Kelvin. And this is data for the bulk thermal expansion with the thoria Syria fuels. And you can see here the coefficient of thermal expansion in terms of ppm per Kelvin. We have studied all this, including this here. The Syria is used as a substitute for plutonium. So you can see here from these numbers the thoria-based fuels show lower thermal expansion, and unlike thermal conductivity, expansion is not significantly altered by UO2 doping. The gray phases, here you can identify, they show higher expansion, and CO2 here is used as a surrogate for plutonia, and rare earth fission products cause higher expansion. The thermochemistry of thoria fuels, this is studied for because during irradiation there are progressively evolving chemical properties like oxygen transport, oxygen potential, fuel, fission product, these interactions, and FCCI, fuel-clad chemical interaction. And also there are physical properties which progressively evolve, that is the fission gas, volatile fission product release, fuel swelling, the fuel-clad mechanical interactions, radiation effect, microstructure evolution, and for this, the thermochemical thermodynamic studies are essential to understand the fuel's chemical behavior and constituent distribution. For this, we have an exhaustive program where we have studied these systems. You can see here the various systems, and the experimental techniques used are the transpiration technique, Knudsen diffusion, isoporable calorimetry, TGDTS studies, and the properties which we have evaluated are the Gibbs energy of formation, standard molar enthalpy of formation, partial pressure of fission gases, the iodine in particular, in fuel-clad gap, chemical diffusion of oxygen, and some of the essential issues what have been brought out from these studies is that the thoria fuels have poor oxygen buffering and transport. There is a high oxygen potential compared to urania fuels. The molybdenum oxidation, which was referred by Dr. Ramkumar, is crucial in regulating oxygen potential. Formation of highly oxidized products like ceria, molybdate, and so on and so forth. Lesser clad corrosion by iodine, tellurium, and cesium, and excessive swelling, that is the fission gas retention and oxygen-rich phase formation. The transport properties of the thoria fuels, that is in particular for the volatile fission products, iodine, tellurium, and fission gas, that is xenon, how this gets distributed. For example, this is a typical schematic thermal profile of HWR pin, and you can see the temperature variation from here to here, and this is a design, this is the fuel pellet, and this is a zircaloy clad there. So the diffusion and accumulation of iodine and tellurium at the fuel clad interface, the buildup of iodine, tellurium, xenon, it can cause the stress corrosion cracking, and also the deterioration of the gap conductivity due to released fission gases, and therefore the diffusion coefficients become very important input for this. And in this case, we have studied these fuels. This is the virgin fuels, and these are sim fuels corresponding to 20 gigawatt day per ton burn up. The fission products probed are xenon, iodine, tellurium, and the methodology followed here is a trace irradiation. It's about 2 into 10 to the power 20 fusions per meter cube. Then post irradiation annealing and radiometric assay. These are two setups here. This is for iodine and tellurium release studies, which are collected on the copper collectors, whereas for xenon, it is the charcoal trapped in liquid nitrogen. And these are the diffusion coefficients that the transport properties we evaluate, and we identify that the poor transport of volatile species, that is iodine, tellurium, cesium in HWR fuels, and there is an excessive swelling due to retention of fission gases and oxygen-rich phases. So in summary, the thoria-based fuels, the indigenous database for the thermophysical, thermochemical, and transport properties has been generated for HWR fuels and sim fuels. Thermochemistry of HWR fuels is different from the PHWR fuels. The oxygen potential and fission gas retention is higher than urania fuels. The fuel fission product compound influence physicochemical behavior. The studies on sim fuels with the extended burn up, this is the work which is under progress, and we're also going ahead with the theoretical simulation of these results. And switch over to the next topic of my presentation. That's the metallic alloy nucleofuels, and they have a crucial role in rapid expansion of nuclear energy. And these are the issues which are well known. There is a substantial experience with the metal fuel reactors from the earlier studies. The faster breeding, ideal for fast reactors, superior transport, proper heat transport, safe irradiation up to high burn-ups, inherent safety. There are additional advantages like electro-refining, water repression resistant, and they can act as minor actinide burners. In the Indian program, first few FBRs, they are the MOX fuel, and they will be followed by metallic fuel FBRs. And what I talked about are the uranium, plutonium, zirconium alloy, which are the choices for this. Now let's look at this, that the metallic fuels have their inherent advantages. At the same time, the thoria fuels have their advantages. The thorium fuel advantage of best nuclear characteristic, sustained availability, economic viability, minimized waste issues, proliferation, resistance, so on and so forth. So if you combine these two issues, one should start looking at the thorium-based metallic fuels. And the advantages are very clear in this view graph. If you take the crystal structure, this is compared for uranium, thorium, and zirconium. In uranium, from room temperature to 1000 degrees Kelvin, there is so many phase transformations which take place, whereas in case of thorium, it is from FCC to BCC at 1633 Kelvin. So there is an isotropic swelling, and it's a better resistance towards FCMI and FCCI. The melting point is higher, so you can have the high temperature operation, high central line temperature, better efficiency, high burn up. Thermal conductivity is good, so it's excellent heat transport. The coefficient of thermal expansion is lower, so lower dimensional swelling. The heat capacity is marginally less, so that is better for transients and LOCA. The hardness is 36, much less than that of uranium. So this is the ease of fuel fabrication, hot, cold working, forging, rolling, etc. is possible. The bulk modulus is small, so metallurgical ease of working, and the density is low. Therefore, the large fission product retention without dimensional instability. But there are challenges with respect to the thorium-based metallic fuel ions. The data is limited. The challenging fuel pin fabrication by injection casting requires higher melting points. One can, in principle, talk in terms of arc melting and initial melting followed by swagging, rolling, but they are not still matured at a large scale. Still possible to do at a laboratory level. Morning, Dr. Day talked about the powder metallurgy. There are challenges to prepare pure metal powders and handling. You require the inert atmosphere. And importantly, the uranium has a limited solubility in thorium, about 1 wet% up to 1273 degrees Kelvin. And then there is a uranium segregation occurs at the grain boundaries. So this is also important, and higher fission gas induced swelling. So what we have started looking at, before that, just look at these phase diagrams, and you can see here, if you take uranium thorium binary system or uranium plutonium binary system up to, let's say, 20% uranium, you can see the solidus temperature is in the range of 1400 degrees centigrade. So that's a very positive thing, except that Pu addition lowers the solidus temperature more than when uranium is added. And there are fuel options are thorium-rich, uranium, thorium, plutonium, so on and so forth. You can have the ternary alloy. And in fact, some of these fuels are proposed for the fast reactors, and some irradiation performances are reported for thorium-10 uranium, thorium-20 uranium, and plutonium alloys. Now, in our laboratories, we have generated this, prepared these thorium-based alloys. These are thorium-10 uranium, thorium-20 uranium, uranium-10 zirconium wet %. Also the ternary alloys, thorium-3 uranium, 7 zirconium, so on and so forth. The method used here is the argon arc melting, and the alloy preparation to the vacuum annealing at 1070 degrees Kelvin. You can see here this is uranium thorium. Of course, they are inherently with some uranium oxide and thorium oxide. Now, the thorium alloy preparation, this is done through the vacuum sintering or arc melting. That this is a powdered thorium, from there to sintered thorium to the arc melted thorium, and these are the different stages. And finally, we arrive at this alloys, and this is the uranium thorium. This is uranium 10 wet % uranium, thorium 20 wet % uranium, and all this material handling has been carried out inside the inert box atmosphere. Now, in the prepared alloys, there is the concern of the non-metallic impurities, and here you can see here that to start with the uranium and thorium, the carbon, oxygen, and nitrogen, this is 1100, 150, 100 and 300, 2200 ppm. But when you form the alloy, you find that after arc melting, the oxygen content increases, the nitrogen content also increases, and the carbon content goes down. Now, we have studied this using the structural characterizations, and you can see here, this is the X-ray XRD of thorium metal, and this is uranium metal, and these two are the thorium-20 uranium and thorium-10 uranium. So, you can really see that the biphasic regions of alpha thorium and alpha uranium in the annealed alloys. The morphology of these alloys, thorium, zirconium, uranium ternary alloys has been studied, and you can see here these dendrite-like structures which indeed correspond to thorium oxide impurity phase. This has been also further investigated using the microstructural characterizations, and you can see the uranium-rich phases there. That is, EDAX indicated the uranium-rich precipitates in the prepared alloy, and this is the further work on uranium, thorium, zirconium alloys, and you can see that alloys with the multi-phase regions, phase segregation around the grain boundaries taking place. You can see it very clearly here. These are the uranium-rich phases here, which are the gray spots here. This is generally the thoria-zirconium-rich phase, and this is zirconium oxide and thorium oxide. The bulk thermal expansion of these alloys has been evaluated, and you can see here, I will just go to the data that has been obtained from our results for thorium metal. This is a number 11.7 into 10 to the power minus 6. The thorium-10 uranium alloy is 11.9 10 to the power minus 6 per Kelvin, and this is 20% uranium is 13.4, and you can see that for pure uranium metal, this is 14.2 into 10 to the power minus 6. So, this lie in between the thorium and uranium values, typical of this biphasic behavior. The specific heat conductivity of these alloys has been measured, and the important point here is that the lower Cp of thorium alloys as compared to the uranium is advantageous for fuel during the transients. The thermal diffusivity measurements have been done through all this. I will not go into the details. And the final results for this, the thermal diffusivity, here you have the thermal diffusivity for the thorium metal, and for uranium metal is somewhere here percent uranium, and the blue one is for thorium-20 uranium. So, thorium has the highest thermal diffusivity, and addition of 10 wet percent uranium does influence the diffusivity, but further uranium incorporation marginally deteriorates it further. And this thermal diffusivity of ternary alloys has been also investigated. This is one important thing which shows the importance of annealing of these alloys. For example, here, this is the first run, you get this data. In the second run, you start getting the other data, and that if you go for the third run, then it saturates. That means the importance of annealing for such alloys is extremely important. The thermal conductivity of alloy fuels has been measured, and this is the consolidated picture here. This is the thorium, this is the uranium, and this thorium, 10 uranium, 20 and 20 uranium lying somewhere here. The take-home message is that the thorium metal shows higher conductivity, systematically deteriorates with uranium addition, and similar results are also obtained for thorium, uranium, and zirconium alloys. How do we look forward? That is thorium-based metallic alloy fuels. The thorium-based metallic alloy, these are the promising candidates for the future reactors. The comprehensive understanding that includes the production, characterization, and physicochemical behavior is the need of the hour. We have initiated the work on the indigenous database for thermophysical, thermodynamic, and transport properties of the metallic fuels, and the evaluation of thorium-based metallic sim fuels, that is the next one that we are going to do, and simultaneous development of both oxides as well as metallic fuels would do good for the nuclear energy program. And also, we have been working on the thorium-based molten salt. Thank you very much, and I acknowledge that this work has been contributed by several of my colleagues in the chemistry group, and they have been working very hard towards generating this indigenous database. Thank you very much.
Thank you, Dr. Jagatap. We can have a couple of questions from the audience. Just one question from me. The sim fuels, what's the meaning of sim fuels? Because I don't know.
Oh, that is for a particular burn-up, whatever is the fission fragment content that you add to the virgin fuel and make a composition. That's the sim fuel.
Okay. Thank you very much. Dr. Jagatap, on behalf of the organizing committee, I would like to present you this memo